Picture this, you've built a wildly successful mobile app. We're talking 100 million users. Amazing, right? Well, there's a huge catch. Every single tap, swipe, and refresh on that app is hammering your backend APIs. If every one of those calls is slow, verbose, and just wildly inconsistent across your Android, iOS, web, and IoT clients, well, your infrastructure isn't just going to creak, it's going to crash. Scaling under those conditions, it's an absolute nightmare. Welcome to this explainer. Today, we're unpacking the source material to tackle this exact visceral scaling problem. We're looking at the high-performance framework purpose-built for hyperscale communication, gRPC. Okay, let's dive right in. Here's our roadmap. First, we'll look at the fundamental problem with REST. Then, we'll break down the gRPC architecture, dig into protobuf and HTTP/2, explore the 4 communication modes, talk about scaling with client SDKs, and wrap it all up with a real-world ride-sharing system design. So, part 1, the problem with REST. Before we can really appreciate the solution here, we gotta understand the bottleneck. Look, standard HTTP/1.1 and JSON have been the absolute backbone of web APIs for years. But at hyperscale, they create massive traffic jams. A standard JSON response is text-based, human-readable, and frankly, it's just super verbose. Sending all those curly braces, quotation marks, and spelled-out keys over the wire just eats up valuable space. But the real hidden cost, the absolute killer, is the heavy string parsing overhead. When your server gets this JSON, it literally has to read it character by character, allocate memory, and parse those strings into native data types. These large, slow-moving JSON packets are just inherently inefficient for the millions of rapid machine-to-machine interactions you need at scale. Oh, and without a strict contract, generating client SDKs turns into a totally manual, error-prone nightmare. Which brings us to part 2. The gRPC architecture. To solve these exact scaling pains, Google engineered a massive paradigm shift. It requires us to completely stop thinking about fetching documents and start thinking about executing functions. gRPC is a high-performance remote procedure call, or RPC framework. The core concept of RPC semantics is just remarkably elegant. It allows your code to call a function on a completely different machine across the network, exactly as if it were a local function running right on your own laptop. You literally just call a function like getProfile, and the framework handles all the heavy lifting, the complex network routing, the serialization, the execution, all entirely under the hood. To make this complex system a bit more digestible, it really helps to view gRPC not just as a tool, but as a sort of progressive equation. Think of it like this: protocol buffers plus HTTP/2 plus those RPC semantics we just talked about. That specific combination is what makes it an absolute powerhouse for modern system design. Let's lay out the foundational pillars that allow this architecture to operate so seamlessly across platforms. First up, you define your APIs in strict.proto files. That's your single source of truth. Second, you use that file to automatically generate all your server and client code. Third, instead of clunky text, you communicate entirely in lightning-fast binary. And fourth, you multiplex all those requests over a single connection. Moving on to part 3, protobuf and HTTP2. Now, what's really interesting about this is how these twin engines power the whole thing. These twin engines are absolutely key to understanding why gRPC completely outpaces REST. When you compare a verbose JSON string with all its spelled-out keys to protocol buffers, or protobuf, the difference is night and day. Protobuf serializes that exact same structured data into a tiny fraction of binary bytes. And the secret sauce here? In protobuf, field numbers matter way more than field names. When you compile your data, it's not sending the string user ID over the network. It just sends a tiny binary tag representing field 1. This guarantees incredibly fast serialization, drastically smaller network payloads, and strict backward compatibility simply because you never, ever reuse a field number. But look, small payloads aren't going to save you if the network highway is completely clogged. Without HTTP/2, requests often have to wait sequentially. If request 1 gets stuck, everything behind it just stops. It's a massive bottleneck known as head-of-line blocking. HTTP/2 swoops in as a total superpower here. It utilizes a single TCP connection and multiplexes all your requests in parallel. Everything travels simultaneously over the exact same wire, completely eliminating that line blocking delay and just drastically reducing your overall latency. All right, let's hit part 4. 4 communication modes. Because we're fully utilizing HTTP/2, we are no longer restricted to that standard, simple request and response model. We get 4 distinct modes. First is unary. This is your classic one request, one response, just like a standard API call. Second, we have server streaming. Here, the client asks once, and the server streams back a continuous flow of responses. Think of a dashboard updating livestock prices. Third is client streaming. This is where the client sends a stream of data and the server just responds once at the very end. That's ideal for uploading massive volumes of analytics logs. And finally, fourth, bidirectional streaming. Both sides are sending streams of data simultaneously and completely independently. Think of a real-time chat app or a highly competitive multiplayer game.
Part 5. Scaling with Client SDKs.
If you've ever worked on a large-scale product, you already know the absolute pain of maintaining consistent SDKs across heavily fragmented platforms. It's tough. But gRPC brilliantly solves this. Because you defined your entire system in that single .proto file, gRPC auto-generates strongly typed clients for you, automatically. You instantly get your Android SDK generated in Kotlin, your iOS SDK in Swift, and your web client in TypeScript. Everyone is working off the exact same strict contract. This drastically reduces bugs, stops that endless miscommunication between backend and frontend teams, and it actually allows your engineers to focus on building features instead of writing repetitive network boilerplate. 100 gigabytes. I want to just pause on that number for a second for impact. When you combine the tiny binary size of protobuf with that auto-generated SDK efficiency, the visceral math of hyperscale really becomes clear. If you save just 1 kilobyte of payload data per request by switching from verbose JSON to protobuf, and you're processing 100 million requests, that translates to 100 gigabytes of saved bandwidth. That is massive. We're talking vastly lower server costs and incredibly faster load times for your end users, especially the ones stuck on poor cellular networks. Now, to be perfectly objective here, we do have to acknowledge the trade-offs. It's not a silver bullet. Direct browser support for gRPC is still somewhat limited without using a proxy, plus debugging binary data is just inherently harder than reading plain text JSON. You also need really strict discipline when evolving your schema, and load balancing those persistent HTTP/2 connections definitely requires specialized proxies. But to handle these complexities, gRPC does offer some incredible advanced built-in reliability features. You get strict deadlines to prevent hanging calls, automatic retries for those annoying transient network failures, and interceptors that act as a clean middleware for things like logging and authentication.
Let's bring this all together in Part 6, Ride-Sharing System Design.
Let's take all this abstract theory and apply it to a massive backend. Think millions of concurrent drivers and riders. And this brilliantly illustrates how those 4 communication modes map directly to active features. When the mobile app calls get nearby drivers, it uses a unary call for fast, simple binary communication. When it hits book ride, it relies on low latency guarantees to secure that transaction instantly. But the real magic happens with track ride. For that, we use a bidirectional stream. The driver's app is constantly streaming their live GPS location up to the server, while the server is simultaneously streaming those exact updates right down to the rider's map. All of this is multiplexed over a single, highly efficient connection. So the crucial point we want you to take away from this explainer is this. If REST is web-friendly communication, gRPC is high-performance systems communication. When things like low latency, high throughput, ironclad API contracts, and seamless multi-language SDK generation actually matter to your business, gRPC is for sure the premier tool for the job. Which leaves us with one final question for you. As you look at your own current infrastructure, maybe those massive JSON endpoints currently buckling under traffic, how will you re-architect your heaviest APIs to handle hyperscale? We hope distilling this source material has given you the blueprint to kick off that transformation. Thanks for joining us for this explainer, and we'll see you next time.